All right, everybody. Sorry, we're having a little bit of recording difficulties with my camera, so we're going to use a different camera for this clip, but hopefully we can get the point across here. So here is a motor. Let's see if we can get it up to the screen. In this segment, we're going to talk about motor specs. Okay, so if you see this motor here, it's a flight test radial on the top, and right here on the bottom it says 1806. If you can see that very well, maybe. Try to zoom in a little bit more here. There we go, 1806, 2280 kV V1. So you say, well, that's a motor. Okay, what do all these numbers mean? 1806, 2280 kV V1, what are you talking about? Okay, so let's explain a little bit of motor specs and what that means. All right, so if we take the top off this motor, okay, we can see the stator, right? And let me grab a measurement device. We're going to measure the stator width and height. That's going to clue us into what that 1806 is actually stands for. So put this over here for a second. Let me grab my micrometer. Okay, here we go. So if we have our motor, try this in a way you can see here. There we go. So if I take my micrometer here and I measure the motor, or the stator, I should say width, like this. Okay, we're going to get a readout of 17.5. Let's make sure I get a good reading there. 18, yeah, about 18, okay. Hint, hint, right? 1806 was the designator on this motor, that first set of four numbers. So 18 is going to represent the stator width in millimeters, okay? And then we have the height of the stator, not counting the coils, so I'm not measuring the copper part, just the kind of the T-post segment here. Oops. I'm going to measure like this, and we get about about 6-ish millimeters if I'm measuring okay accuracy level wise here. I get about 6 millimeters of height on the stator. Okay, so again, 1806, grab that. Okay. Let's get that. There we go. 1806, 2280 kV V1. So the 1806 is a 4-digit number, and basically the first two digits refer to the stator height in millimeters, and the second two digits refer to the stator, the first two digits are the stator width. My mistake there. First two digits are the stator width in millimeters, and the second two digits are the stator height in millimeters. In this case, 06 just stands for 6. Now, sometimes you'll see motors that have an extra decimal, like a 2205.5. Okay, so you can kind of attribute that decimal to the height of the stator. So if this was an 1806.5, that would mean the stator was 6.5 millimeters high instead of just 6 millimeters high. I don't think I've ever seen one with a decimal place as far as the stator width goes. I guess it could exist, but the only time I've ever seen that is on the stator height. Okay, 0.5 of a millimeter is not that big of a difference, right? But there are motors out there that designate it to that level of precision. Okay, so there's our first set of numbers, right? And what's the second set of numbers? 2280 kV. Okay, we don't care about V1. That's just a marketing thing from Flight Test. This is their version 1. But 2280 kV, that is important, right? So the kV number, we'll see 2280 here. Let me grab another motor and see if we can look at that. Here's the big motor that we looked at earlier. So it says kV 400. Okay, where's that little teeny tiny motor? Here it is. Here's the top of it anyways. Okay. And then we have, let's see here, Mamba system. You can see that. Come on, camera. There we go. 6500 kV right there. We have 1103. Okay. So all these motors have similar types of numbering systems, right? This is a 3515. That means 35 across, 15 tall on the stator, which is right here. Okay, so if I were to measure this across, I'd measure it across this way. 35. There we go. And then we can measure the height, about 15. Okay. Same thing for this teeny tiny motor. And it's an 1103, so if we measure across, oops, sorry, we should get about 11. And if we try to measure the height of the stator, we'll get really small. There we go. About 3 millimeters. Okay. So the first set of numbers is, again, the height and width of, or the width and height of the stator. The second set of numbers we're looking at here, the 2280 on this motor here. There we go, 2280, okay. 3515 on this big guy here, or not, sorry, not 3515, 400 on this one for the kV. Okay. On the little one here, we had 6500, right? So roughly what happens, let's see here, get the focus. Okay. There we go, 6500 kV. Okay. So what that means is basically when you apply a voltage to this motor, so let's say in a theoretical world, okay, I'll flip back over to the slides here for a second. Okay, here is a slide that kind of breaks this down. The kV is talking about RPM per volt, okay? There's more math behind it, but that's kind of the rule of thumb. So if you have a motor that has a kV of 2380, which was what this, 2280, what the flight test motor was, that means basically, theoretically, if I applied a voltage of 1 volt to that motor without a prop on it, so unloaded, okay, the motor would spin 2,280 RPM, okay, because I applied a 1 volt. We have another example here in the PowerPoint. A 980 kV motor, okay, would spin at 10,878 RPM if it had an 11.1 volt battery applied to it, which would make a 3-cell battery. Okay, but basically it's RPM per volt. So whatever kV says, if you were to apply 1 volt to that motor without any prop on, theoretically that's how fast it would go. And if you scale it up to a normal battery voltage, say a 3-cell, 4-cell, 6-cell battery, you would multiply the kV by the battery voltage to get the RPM that motor should theoretically spin if there's no propeller attached. Okay, and that's a way to kind of compare across motors because you can put different props on the same motor, right? So you can't measure it with a prop on because then you have to know what prop it is. We measure it unloaded, that way we can compare across all different motors. And basically you can have motors of the same physical size that have different kVs. That's based on the number of windings, the thickness of the wire in the windings, the magnets. So lots of different factors go into the kV, but essentially the higher the kV, typically the faster that motor is meant to spin, right? And the lower the kV, the slower that motor is meant to spin or designed to spin. We say, wouldn't you always want the motor supposed to spin faster? You know, oftentimes you might want something like that, but some motors are designed to spin really big propellers on large aircraft, and those propellers don't need to spin so fast to be efficient and generate a lot of thrust. But they do have to, they are heavy, and so the motors have to have a lot of torque. So typically you go lower in the kV range, your motor is going to be slower but have more torque. Higher in the kV range, your motor will have less torque, but it will be a faster spinning motor. And so again, if we look at if we compare the motors I've been showing you on the dot cam here, let's go back. Is it this one? Yeah. Okay, so if we compare the motors we've been looking at, this really small one, let's see here. Oops, a little bit farther. Sorry, getting used to the camera here. And these 3 motors here, we have our little guy, bigger, right? This is 6500 kV. This one is 2280 kV, and this one here is 400 kV. Okay, so which one spins the fastest? Typically this one would be the one that spins the fastest, right? 6500 kV. But the prop you would put on this type of motor is very, very small. You know, less than a few inches across. This one here, 2280 kV, you can spin maybe a 4 or 5 inch propeller typically on that kind of motor. Okay, this one is 400 kV, meant to spin a very large prop. Well, I don't know, maybe 15 inches in diameter or something like that. Okay, so this one's not going to spin as fast, but it'll spin a much larger prop. And then we kind of trade off from there. Smaller prop, faster, even smaller prop, even faster. Okay, and if you have a really small prop, you kind of have to spin it relatively fast to get any thrust out of it, right? It doesn't have as much surface area. So hopefully that helps explain, let's go back to the slide here. Hopefully help explain this a little bit as far as this motor specs go. When you're looking at motors, you will see those numbers, the set of numbers there, the first set there, in our case an 1806 on that flight test motor, and that's the stator diameter, and then the stator height, okay, in millimeters. And the second number that's usually the most important besides the motor size itself, is the kV, so RPM per volt. With those two specs, you can pretty much figure out what most motors are talking about and compare them to each other. Some manufacturers will give you additional information on the motors you can add to your research, but if you know at least these two things, you're pretty good as far as comparison-wise. Okay. You will also want to pay attention to, let's go back to this, the motor mount pattern. Okay, so the holes here, how far away they are from each other, what's the measurement, right? Different measurements for different size motors are kind of standardized, but they're not always exactly the same. You can see this one's asymmetrical. Okay, and they have a smaller mounting pattern here. And what size screws go into those holes, because all that has to match up with how you're going to mount it on the aircraft, right? You can't just grab this one and stick it on a little tiny aircraft. There's no way to mount this motor. It's too big, right? Something we haven't discussed as much, but you can kind of see is present here a little bit on some of these motors. Put a couple of these back together here. If you look on this big one, okay, the motor shaft just sticks out a little bit, just enough to kind of slide a prop onto there, but there's no like nut to tighten down the prop, because typically these large props will have holes drilled in them that you then put screws through to attach the screw to the motor bell or the motor or the rotor. Okay, that's also the case on this little guy actually. So it's got a little teeny tiny motor shaft. Okay, and we have little small holes there. I'm not sure if you can see those very well. There's little holes to either side of the motor shaft, and you would put a small prop on there and you put screws through the prop and tighten it down to attach it to the motor bell. Okay, there's no threads on this motor shaft. It's just a smooth shaft. Okay. However, on this guy, we have threads on the motor shaft. There we go. And since we have threads on the motor shaft, we would put the prop on and then we'd put a nut on here and tighten the nut down to kind of force the prop to stay on the motor. There's no other holes in the motor bell to attach the prop with. It's just basically based on the compression force of the nut crushing down on that prop to hold it in place on top of the motor. And so there are different ways to attach your props. You want to pay attention to that as well when you're buying propellers, as well as when you're buying motors. If you have a preference, then you want to pick that option. All right, we'll see you in the next video.